Hello and welcome to Module 5 of the Consilium Aquis Sulis course on railway signalling. This module begins by answering the question, what is an interlocking? It then describes the evolution of interlockings and finally provides an overview of railway control systems. In principle, a railway signalling interlocking is a device to mitigate the risk of signaller error leading to a collision or derailment. It ensures that trains are only authorized to move when it is safe to do so. Authorizations, whether issued by signals or electronically, are appropriate for the movement and movable infrastructure, such as points, is locked in positions safe for the passage of trains authorized to travel over it. However, the role of interlockings has evolved considerably since they were first conceived. The first interlockings were mechanical devices that prevented signallers from moving levers, controlling signals and points in unsafe combinations and sequences. By contrast, electromechanical interlockings, introduced in the 20th century, controlled signals and points directly. Relay circuits switched electrical power to illuminate signal lamps and move points via electric motors when safe to do so. Instead of moving points and signals directly, signallers simply request routes from one signal to another, or even request signals to work automatically. Computer-based interlockings continue to directly control points and signals or the issue of electronic movement authorities. Taking advantage of greater processing power, new functionality to mitigate specific safety risks and meet specific operational needs has also been introduced. The introduction of computer control systems further expanded the role of the interlocking to support new functionality. Like interlockings, control systems have evolved considerably over the history of railway signalling, with a trend towards greater centralization and greater automation. Greater centralization enables more strategic operational decision-making, as decisions can be made in the context of a greater area of railway. Greater automation enables each signaller to control a larger area. The first control systems were mechanical level frames in signal boxes, each controlling a single junction. The advent of electromechanical interlockings enabled the task of moving individual points and changing signal aspects to be automated. The signaller now simply requests the route from one signal to another on a control panel or VDU screen. Route setting functionality, whether with electromechanical or computer-based interlockings, enables routes to be set much more quickly. By reducing the signaller's workload per route, it also enables signallers to control larger areas. This delivers benefits in terms of improved capacity, greater ability to make strategic regulation decisions, and reduction in staffing costs. On some lines, signallers do not even set routes for most train services. The routes are instead set automatically in accordance with the timetable or algorithms. One of the earliest technologies to do this was the program machine, introduced onto London Underground in the 1950s. Program machines were electromechanical devices that commanded interlockings to set routes in accordance with the timetable as trains approached. Towards the end of the 20th century, computer-based technologies for setting routes automatically began to be deployed on metros and main lines. Like program machines, they can set routes in accordance with timetables. However, they can control much larger areas and more complex timetables than program machines, enabling their use on mainline railways. They also support the addition and removal of services and can make basic regulation decisions when services are running late. In order to route a train service correctly, whether manually or automatically, it is necessary to know what service it is. Originally, services were identified by means of specific configurations of lamps displayed on the front of locomotives. Information about approaching trains was also communicated between adjacent signal boxes by bell codes. Train services are now identified by numeric or alphanumeric head codes. Originally, these were displayed in large letters on the front of trains. In modern signaling systems, head codes are presented directly to signalers on their control screen or panel by devices known as train describers. As a train moves through the schematic representation of the railway layout, so its head code moves with it. At the start of each journey of a train service, its head code is entered into the train describer. When train detection indicates that the train has moved into an adjacent section of track, the train describer moves its head code into that section. Train describers in different signaling control areas communicate with one another so that head codes follow services seamlessly throughout their journeys. As well as requiring routes to be set through railway layouts, train services require appropriate rolling stock to be available at the start of their journey. There are many different types of rolling stock, including locomotives, wagons, carriages, multiple units, rail cars, and engineering vehicles. Rolling stock periodically requires maintenance and cleaning. Diesel-powered rolling stock requires refueling. Tracking rolling stock and providing the required vehicles at the required place and time for services is the job of rolling stock management systems. Most train services require staff to operate them. Staff have different competencies, often connected to specific types of rolling stock and routes. They are also rostered to work specific shifts, starting and ending in specific locations. Ensuring that suitably competent staff are available when and where required to operate services is the job of train crew management systems. In summary, interlockings mitigate the risk of signaler error by ensuring that infrastructure is only moved and trains authorized to move when it is safe to do so. Modern interlockings directly control the movement of points and issue of movement authorities, whether via signal aspects or electronically. Signalers either request routes from one signal to another or oversee algorithms that set routes automatically. Train services are identified by head codes presented to signalers on their control screen or panel by devices known as train describers. Rolling stock management systems track rolling stock and providing the required vehicles at the required place and time for services. Train crew management systems ensure that suitably competent staff are available when and where required to operate services.